Okay. So thank you again for coming to another installment of Quantum Fluids in Isolation. So this week we have Pramodh Yapa from University of Alberta in Canada. Pramodh got his bachelor's degree from Carleton University in Ottawa in 2015, his master's degree in condensed matter theory from University of Victoria in Victoria, British Columbia in 2018, and now he is currently a PhD student at the University of Alberta studying condensed matter theory. And most recently, in 2018, he was the winner of the Dance Your PhD competition by Science Magazine and AAAS. And today he'll be talking about superfluid helium-3 and the confines. So please help me in welcoming, either by unmuting yourselves or virtually, Mr. Pramodh Yapa.
Excellent. Thank you so much for the introduction, Joshua. And I unfortunately will not be dancing any of my results or any of this talk today. And thank you for the invite to come talk here, because it's been a wonderful seminar series. I've been attending these talks since I think when you started back in April. And to be honest, it's been a little intimidating to give one of these talks, given all of the stellar speakers that we've had. I think there have been some like actual giants in the field. So I am actually a fairly new, a bit of a newcomer to the quantum fluids community. As Joshua said, I only started thinking about superfluids once I came to the University of Alberta and started this project on superfluid helium-3. But in that time, I've become so enamored by helium-3 as a system that I've been kind of shouting its virtues from the rooftops. And I'm glad to come here and share some of my excitement about superfluid helium-3 with you today. What I want to do today is talk about what makes superfluid helium special, and especially what makes it special when you confine it, when you put it into a slab. So you have boundaries. So this interaction between the superfluid helium and the boundaries brings up some really novel effects, some new properties. Now, superfluid helium-3 itself is a really interesting system because it has all these extra internal symmetries, and these internal symmetries that you can break to produce different superfluid phases. And these different phases have properties that you can think about in analogy to superconductivity. And then you can think about other properties related to pneumatic liquid crystals. You can think about it in relation to antiferromagnets. So there are a lot of analogies that superfluid helium has to other condensed matter properties. So it's a bit of a window into pretty much any of the techniques that can be used in condensed matter. So I want to give a little bit of an introduction to superfluid helium itself. I want to obviously talk about some of the work that's been going on at the University of Alberta with regard to helium-3, but this is kind of more a survey of all the amazing things that happen when you confine superfluid helium-3. Actually, I was gonna put on captions here, so let me do that right now and get the pointer. As it says right here at the bottom, you can ask me questions anytime during the talk. Just pipe up. Don't be afraid to interrupt. I'm happy to take questions. So let me start off by acknowledging all the people who have been working on superfluid helium at the U of A. This entire project, pretty much what I've been working on, was nucleated by John Davis. This is his group here. He's in the audience. Him and his group, so Alex Shook, Callum Doolin, Vaisak Vadakumbat, Emil Varga, they've been doing some amazing work with putting superfluid helium-3 in really confined geometries and seeing what comes up. And it was, them wanting some sort of input on some of their experimental results that led me down this path, and led my supervisor, Professor Joseph Pacheco, Rufus, who's also here, for us to kind of contribute to the efforts on the theory side. Obviously, I want to thank some of the founding bodies, funding bodies, Quantum Alberta, TPI, Alberta Innovates, and the university for funding all of this research into superfluid helium. Let me start off with a bit of a prologue, actually. So what you see here is a phase diagram for superfluid helium-3. If you're used to helium-4, you may notice that this axis down here is very different. So superfluid helium-3 becomes a superfluid at temperatures less than about 2.5 millikelvin, which is 1,000-fold lower than helium-4. And this all has to do with the pairing mechanism that causes the helium-3 to condense. The pressure here goes up to 30 bar. Above this, it's a solid, but all the way down to 0 temperature within this pressure range, superfluid helium, helium-3 is in a superfluid phase. Now, these two bulk phases, so you'll see these two different colors, and these different colors relate to two different distinct superfluid phases. And both of these phases were discovered in 1972 by David Lee, Doug Ostroff, and Bob Richardson. And in doing some research for giving this talk, I found this amazing anecdote by Bob Richardson in Physics Today. So this is about 10 years after they found these two phases. And he kind of recounts this talk he went to see in 1961, given by Brian Pippard, actually Sir Brian Pippard. If you're familiar with superconductivity, Brian Pippard is kind of a giant in the field. And so Brian Pippard was giving this talk, and essentially what he was saying is that over the next 10 years, from 1961 onwards, he was expecting that all of the big questions in low temperature physics would be answered. So liquid helium, superconductivity, magnetoresistance. He was saying in 10 years, they're going to, see the end of pure physics being done in the low temperature regime. And I love this quote: "The last generation of settlers in the new land of physics found it green and fertile. We shall leave it a dust bowl." So Brian Pippard was very cynical about the future of low temperature physics, but obviously almost exactly 10 years after, these three found this entirely new behavior in superfluid helium. And obviously we're here still talking about liquid helium. We're still talking about superconductivity. We're still talking about magnetoresistance. So there's a lot still to be done in low temperature physics, and a lot of fundamental physics has come up. And especially in helium-3, I would argue there's been a lot of fundamentally new things that have come up when you consider these helium in confined spaces. So fast forward from this 1972 diagram to in January, where we published this paper. This is mostly an experimental paper. All the hard work was done by John's group here. And this was essentially a phase diagram over the same temperature and pressure range. And the difference is that John and his group put helium in a slab. So they had these devices that could confine the helium in one direction, in the Z direction, in the Z direction here, to about less than a micrometer. This phase diagram is for 636 nanometers. So you have confinement in this direction, and it's pretty much effectively infinite in these two directions. And in trying to find new phase transitions, so sweeping from high temperatures to low temperatures, if you were looking at the bulk phase diagram, what you would expect to see is two phase transitions. So a phase transition from the normal liquid state of the helium into the A phase, and from the A phase into the B phase. And obviously, just by looking at this diagram, you can see that was not what they found. Three phase transitions were found upon cooling and warming. So a new superfluid phase in gray appeared. So we did some like mild theory calculations to figure out, okay, so the first phase transition was definitely into the A phase. The last phase transition, if you're going this way, was into the B phase. This middle phase is something completely new. So the question is, what is this new phase? So kind of the rationale for doing this confined helium experiment, though, was some theory work that had been done in the last 10-ish years that showed that this was probably something called a pair density wave state. And the way to think about it is that this is actually a spatially modulated phase. You could almost call it a superfluid crystalline state of matter. So the A phase and B phase, as we know it in bulk helium, is a spatially homogeneous phase. There's no spatial dependence of the order parameter. But this phase, there's good reason to think that it is a periodic pair density wave state. And so I want to talk to you about why we think this pair density wave appears. And I also want to tell you about some cool physics that happens when you consider, okay, you have this state, and you also have this B phase interacting with the boundaries, the bottom and top boundaries, which can lead to the formation of some new bound states and some new collective modes. Okay, so let's pull back. Let's talk about pair density wave states. Let's not even think about superfluid helium. Let's think about what is a pair density wave state itself, and how it relates to this FFLO state in superconductivity. So a pair density wave state is actually fairly simple. The way you think about it is an order parameter that varies periodically as a function of the position. So if that, so here's a picture representing that. So this is plotting a unidirectional pair density wave state where the order parameter varies in the x direction. So if you think of this cosine, the cosine is positive, the order parameter is positive here, goes to 0, which is a domain wall, becomes negative, domain wall, positive. So very simple, intuitive picture of what it is, actually, just a cosine modulation and in the order parameter. You can also think about what happens when you take away a domain wall. How do you continuously deform these two states? And if you're going from a negative to a positive continuously, you actually have, you're acquiring a phase winding. And in pair density wave states, you can actually have something that's called a half quantum vortex, because you can see the phase to go from minus to a positive will need to wind by just pi, a pi phase winding. So if you want to learn a little bit more about what pair density wave states are, there's some great review. There is a great review article by Fradkin and Kivelson and a whole bunch of people about pair density wave states, not really in superfluids, but in cold atom systems and in the cuprates, because that's where there's kind of some experimental motivation to see this kind of state. If we try to think about how do we get a pair density wave state in a superconductor, in conventional superconductivity, you have S wave spin singlet Cooper pairing. What this means is if you're considering near the Fermi surfaces, two electrons near the Fermi surface with opposite spins and opposite momenta pairing together. So if you're considering what is the center of mass momentum of these, well, you can add up these two and see that they have a 0 center of mass. That Cooper pair has no center of mass momentum, actually. And this is what actually leads to the spatially homogeneous phase. Having no center of mass momentum means that the order parameter is going to be constant throughout space. And then you can think about, okay, how can we now induce some inhomogeneity in space? And this is where these seminal papers by Fulda-Farrell and Larkin of Chinnikov came out, which considered strong magnetic fields. So taking a superconductor, putting it in a strong magnetic field, and this actually leads to a separation of the Fermi surfaces. So you can think about one Fermi surface for spin up electrons, another Fermi surface for the spin down electrons. And now if you want to pair up and down electrons, you can pair them, but this leads to a finite center of mass momentum. And this finite center of mass momentum, this difference between this P1 and P2 vector that's shown here, is what leads to spatial inhomogeneity. So the FF state and LO state are actually slightly different things. The FF state actually is a cosine spatial modulation, while the LO state varies its phase in space. But again, this is a magnetized induced spatial modulation. And the question is, can we see this kind of spontaneous translation symmetry breaking? Because once you have this periodic behavior, can you see a spontaneous translation symmetry breaking in a superfluid? And well, I mean, I guess I've given away the punchline to that because we think we've already seen it. But I want to give you the motivation of why we think that is possible in a superfluid. Okay, so now let's come to the superfluid itself. I'll tell you a little bit about the bulk superfluid phases, the pairing it has, the internal symmetries, and the two phases that I showed on the phase diagram, which are stable. So helium-3 atoms have a hard core. So you can think about there being really, a lot of repulsion as you make the radial distance smaller, and there is a small attractive well at some distance away from the center of the atom. What this means is that if you want to create a pair, the pair wave function cannot be peaked right in the middle at r equals 0, the radial distance between the two helium atoms being 0. It can't be peaked there. So S-wave pairing is out the window. So you actually, because of this hardcore repulsion, find that the Cooper pairing in helium-3 must be p-wave pairing. So L equals 1 angular momentum. So this is a kind of a cartoon picture of what that looks like. It is an odd wave function. The Cooper pair wave function is odd in space. And because pair wave functions must be asymmetric upon interchange, these are fermionic statistics, this being odd dictates that the spin wave function must be even. So S equals 0 is out now, and S equals 1, the spin triplet pairing, is what is favored. So this is what people mean when you may have heard helium-3 is a p-wave spin triplet superfluid because of this hardcore repulsion. Okay, so now that we have this pairing idea, I want to talk more in terms of the order parameter. For normal S-wave spin singlet pairing, if you're considering the Hamiltonian, the pairing happens because of off-diagonal components, so in the BDG Hamiltonian. And for normal conventional superconductivity, the order parameter is just one complex valued function or number. When we get to S equals 1, L equals 1 superfluid, p-wave spin triplet superfluids, you need an order parameter for each combination of the spin degrees of freedom and orbital angular momentum degrees of freedom. So you can think about when you're considering a Cooper pair, you can kind of visualize it as having a vector for the angular momentum and another vector for the spin. And you can think about the three different projections of that spin. And to account for all these different things, the order parameter, instead of being a complex valued, just a complex valued function or number, you actually have a matrix structure. So it's a 9 complex valued order parameters corresponding to 3 degrees of spin and 3 degrees of orbital freedom. And it varies in momentum space. So what it looks like is you can just put it into a 3x3 matrix of complex valued and all of complex values. And all of these are different order parameters for the superfluid phase. So you can kind of, this is not necessary, but because of all this extra freedom, you now have a vector for angular momentum and a vector for spin. You can think about the symmetries that are broken when you go into the superfluid state. For normal superconductors, you just have phase coherence. So the superconductor just picks a phase, which breaks a U1 symmetry. But now that you have an angular momentum vector and a spin vector, you can think about breaking these independent rotations of these vectors by the superfluid phase. And people have done that. They've just, instead of ignoring, you can ignore all the physics and just do a group theory analysis saying, here are the order, here are the symmetries of the normal phase. How can we break this down into residual symmetries? And you can make this huge list of different phases that can be you can think of by thinking of different order parameters here. But this is unnecessary because we've already seen the phase diagram for bulk helium, and we know there are actually only two different superfluid phases. So let me quickly tell you what those two are. This pinkish phase here is what's called the A phase. And it's an anisotropic phase because if you look at this kind of momentum space representation of the gap that the quasiparticles have, there is a gap in the kx, the ky direction, and it's the same there, but there is a node in kind of the z direction, if you will. So you can excite quasiparticles for no energy just in one direction. So there are a bunch of really interesting things about the A phase, but I won't get too much into that. If you're curious about the symmetries it breaks, so you break this independent rotation of orbital angular momentum spin into, you can rotate around one axis, you can rotate both the angular momentum and then compensate with some phase change. So there's some interesting group theory analysis you can do about this phase, but I don't really want to talk about the A phase. So let me talk about the B phase really quickly. So the B phase is an isotropic phase. So that means if you're looking in momentum space, there's no preferred direction. There is a gap that is the same no matter which direction you look. There's also a phase with zero total angular momentum. You can think about this in, you have an S equals 1, L equals 1 state. When you add those up, well, you can get total angular momentum equal to 0, 1, or 2. And it's just that this phase happens to be a J equals 0 total angular momentum. And you can see all of these order parameters are the same. So really, even though you have a 3x3 structure, you really only have one independent component here. The quick breakdown of the normal symmetry is that instead of being able to independently rotate the spin vector and the angular momentum vector, you have to now rotate those things together in space. So you can rotate both at the same time, but you cannot move one with respect to the other. So there's kind of a fixed angle between them. Okay, so that was a really quick run through the bulk superfluid phases, but where it becomes interesting for us now is what happens to these superfluid phases when you put it into a confined geometry. When you put it into a slab and you kind of squish it in one spatial dimension, what happens to the order parameter? What happens to quasiparticles that interact with the boundaries? Can this lead to bound states? So that's what I want to get into now. And I want to specifically do it for the B phase. I won't talk about the A phase that much. Let's look at what happens to the B phase when you put it in a slab. So the name for this, this phase that's analogous to the bulk B phase is the planar distorted B phase. And if you look at how the order parameter changes, here is the bulk B phase. Now, if you're putting it in a slab, you expect, yes, it will have some spatial dependence now because you're confining it in the Z direction. But what also happens is instead of having just one degree of freedom here, now you split the order parameter into two different things. You have the delta parallel part and a delta perpendicular part. And if you want a plot, if we assume that there is specular surfaces here, so it reflects perfectly at these boundaries, quasiparticles are reflected perfectly at these boundaries, here's a plot of what these functions look like across this gap. So this axis is the Z direction here. And you can see the delta parallel part doesn't actually change when you go from the bulk into the slab. It's fairly constant throughout the slab. And this component, which is in red, actually goes to 0 at the boundaries. So the order parameter is suppressed completely at the boundary, at the Z boundary here. And we can understand this through thinking about pair breaking at surfaces. So think about the quasiparticles that are in the superfluid. They're Cooper paired with equal an opposite momentum. So you have a negative p quasi-particle paired together. Now, if you think of a quasi-particle coming along and hitting the boundary, so imagine it is impinging upon this top boundary over here, and it gets reflected specularly. So it gets reflected this way. Now, since this boundary, reflects only in the z direction, the pz component of the momentum changes. Px, py doesn't change, but pz becomes negative pz. And of course, you no longer have this equivalent opposite momentum. The momentum state of this quasi-particle has changed, and therefore it's no longer Cooper paired. So this is what we mean by pair breaking. The reflection at boundaries causes the Cooper pair to break up, and that's what causes this gap to go to zero at the boundary. Now, in contrast, a quasi-particle just going through the middle encounters no boundaries. So the order parameter is not suppressed when it's in the bulk because it's not reflected. So specular reflection at surfaces leads to suppression of the order parameter. And you can see this in the gap, whereas you had in the bulk a isotropic gap. Now you kind of think about, as you squish the helium in the z direction, the gap also gets squished in the pz direction. And why doesn't these get suppressed at the boundary? It's because of how the gap function works. This order parameter is coupled to the pz components, while these two are coupled to px, py, and thus they are not suppressed. Now, this quasi-particle scattering is also useful for us to think about bound states. So, do you have a question?
So over here, you say how the pz component gets reflected across the boundary, right? So I imagine there's going to be equal number of carriers moving left and right. So if one of them gets reflected to minus p, there's going to be another one which is already moving at minus pz, and that got reflected to pz. Now, can the two of those pair up?
Yes. Yeah, I think there you can pair it up that way for sure. Yeah, that's a good question. Yeah, I'll have to think about that. But so I think it doesn't compensate basically, depending on how you think about it. You do have this quasi-particle. The pair is broken, and which leads to kind of a suppression right at this gap. I don't know if that completely answers your question. It's a good question. I might have to think about how that fits into this picture later.
They can repair, but the pair is already broken, right?
Yeah, but then you would think maybe it wouldn't go completely to zero. But
yes, that's what I thought. Yeah.
Yeah. Yeah, I'll need to think a little bit more about that.
Okay, thank you.
Yeah. So this picture of quasi-particle scattering, you can also let you think about bound states. So this order parameter, in a way, acts as the potential that a quasi-particle experiences. And when you think about the potential that a quasi-particle experiences when it's in the middle versus at the edge, since this delta perpendicular part goes to zero, the potential it experiences at the surface is actually much less than in the bulk. So you form a bound state near the surface of the boundary. So scattering leads to subgap states. Now, this is called Andreev bound states in superconductivity. So if you're familiar with the situation that happens when you consider a superconductor and a normal metal interface, you get bound states there because of, and it's the exact same analogous situation, but taken into a superfluid context that happens. You form bound states that live at the surface where the orbiter parameter is suppressed. And the kind of the picture to think about is when you have a bulk superfluid, you can't have any states in the gap. So you have this continuum of states above the gap and nothing in between. And as you start confining it more and more, states drop out from the continuum into the gap that can be occupied. And these are these Andreev bound states. Now, this Andreev bound states in superfluid helium has been known for a little while, but it was only about in 2009 that people realized that if you consider a special Andreev bound state in the subgap, in the gap, if you have a bound state that sits exactly in the middle of the gap at zero energy, this is actually not a Dirac fermion. It's a surface, it's a Majorana fermion that lives on the surface. So this fermion, I mean, this schematic picture is kind of misleading. What you actually have is a Majorana fermion that's bound to the surface, yes, but it can move in this direction and in that direction. So it's free to move in the XY plane, but it's bound to the surface. So what you have is kind of a Majorana cone. Yeah, this Majorana can roam about bound to the surface. And this is relatively new, even though people knew about the order parameter of helium. The existence of a Majorana fermion on the surface of helium-3 is a fairly new idea. So we can think of particles, so these Majorana fermions that appear on the boundary, but you can also consider fluctuations. You can consider bosons. Can we think of bosons that would appear in the superfluid state? So this is kind of an idea that's been pushed hard by Volovic. He's actually written a book called Universe in a Helium Droplet, which kind of thinks of the analogies between high energy particle physics and thinking about how do those exact same physics of particle physics appear in a helium-3 and helium-4 context. And the way to think about this is you can consider the planar distorted B phase, kind of the equilibrium phase that is stable in a slab, as a superfluid vacuum, and think about what can we excite around that vacuum. And these are bosonic modes, because we're still considering this order parameter, and we can think about, okay, how can I perturb this order parameter around the structure? Well, I can add a real function over here, a real small real function. I can add a small imaginary function here, or I can add them in combination. So you're considering small fluctuations about this equilibrium order parameter. And you can do this in a much more organized way, which is to think about, okay, so this is a 3x3 matrix. You can perturb it, these components, the 9 real components and 9 imaginary components separately. And you can classify these modes by total angular momentum. The equilibrium state of the B phase is a J = 0 mode, and any excitations above this can also be classified in the same way. So S = 1, L = 1 means that you can have a J = 0, J = 1, J = 2, and all of the MJ modes of that. So you have these 18 different bosonic modes that can appear as an excitation in planar distorted B phase. So for example, you can think about a mode that only adds a real part to the delta perpendicular part. This would be an MJ = 0 mode. You can think about perturbing this and this component, and that would be an MJ = 2 mode. So you have all of these different modes, and you can consider, okay, how hard is it to excite them out of this superfluid vacuum? And you can classify them in kind of analogy to particle physics. You can think of Goldstone bosons. You can think of Higgs modes. So if you have a gapless mode, it doesn't take any energy to excite it at all. You have Goldstone modes in your helium-3 system. If there is a gap to these modes, these are analogous to the Higgs. So these are called the Higgs modes. And so what you find is that you now have this system where you have both fermions, Dirac fermions, Majorana fermions, and bosonic collective modes that live more in the bulk. And you can treat them as dynamical fields that can interact with each other. And so I can just point out this quick paper. This was done by my supervisor actually a few years ago, which looked at the surface bound Majorana fermions and asked, okay, if we treat the superfluid vacuum as a dynamical field that can interact, what are the interactions that are possible with all these bosonic collective modes? And the result of that is that this surface bound Majorana fermions that live on the top of helium-3 actually interact through a bosonic Goldstone mode that lives in the bulk of the superfluid helium-3. So a lot of interesting physics that has just only within the last 10 years come about, even though we've known about the order parameter of superfluid helium since the 70s or 80s. So interesting physics there, but I guess let me pull back and think about the original question I posed about the pair density wave state. So the new state that showed up in the phase diagram of helium-3. Can we understand this in the same way? And there is actually a simple argument to be given via quasi-particle scattering that leads to spontaneous translation symmetry breaking, or the pair density wave state. So, this was the picture we had of a quasi-particle hitting this top surface, getting specularly reflected off, getting scattered to a negative PZ momentum state, and that pair is broken. And then we can think about, okay, what can the system do to make sure this pair, at least at the surface, is not broken? And one way this can be done is by considering a domain wall, which separates different order parameters. So let's consider this portion of space having plus a positive delta Z delta perpendicular component, and this side having a negative delta perpendicular component separated by a domain wall. Now, a quasi-particle that scatters over here and gets specularly reflected, obviously, is getting a negative PZ. It's scattered into a negative PZ component. But the potential it experiences, the superfluid order parameter it experiences, is now a negative delta perpendicular. So the negative that comes from specular reflection and the negative that comes from this order parameter cancel out. And actually, this quasi-particle remains in the exact same momentum state because of this now different order parameter it experiences. So pair breaking does not happen if you can form a domain wall that separates two different B-phase vacuums. Now, obviously, this is good for the surface, the quasi-particle that scatters off the surface. But now you think about any quasi-particle that goes through the bulk. It doesn't actually encounter a surface. When it goes through this domain wall, it's none of its momentum components change, but it now goes from a positive delta perpendicular to a negative delta perpendicular order parameter, and that causes its momentum in the PZ direction to flip, and any quasi-particle going through the bulk is now pair broken. So we can think about formation of a domain wall separating two different B phases as preventing pair breaking at the boundary at the expense of pair breaking within the bulk. And so this kind of gives us a way to think about why you would get a PDW phase in superfluid helium at small confinements. It's because the system is now trying to figure out, okay, if we can make pair breaking, we can suppress pair breaking at the surface at the cost of pair breaking in the bulk. And obviously, as you squish the superfluid helium more and more, there is more surface than bulk for some range of thicknesses. And this competition between the reduction of pair breaking at the surface versus the bulk becomes favorable at small confinements. And so what you'll find is that confining superfluid helium in that direction can actually lead to the stable formation of domain walls in the XY plane. And this is kind of the energetic argument towards why a PDW phase can form in superfluid helium-3. Now, there are lots of arguments for this, but it's still unclear what exactly the order parameter of this PDW phase is. So there are some heuristic arguments for the stiffness phase, but there's a lot of work to be done with figuring out, okay, what is the PDW phase exactly? And then you can start asking questions like, how does this PDW phase interact with the fermions and bosons that I explained before in the system? Because so the Majorana fermions formed at the surface of the helium-3 because the order parameter is suppressed at the surface. Now, if you have domain walls, same thing is happening, but instead of happening at this Z plane, it's happening completely within the XY plane as well. So you have portions, you have actually periodic domain walls where the order parameter is suppressed. So you can ask questions like, could Majorana fermions live on the domain walls that form in the PDW phase? How does that affect the collective modes that form in the bosons that kind of form in the planar distorted B phase? How do those bosonic modes change once you go to a planar distorted, a PDW phase? So there are a lot of different questions that are coming up when you consider confinement in superfluid helium-3. And I think I'm going to start wrapping up there. So in summary, we looked at confinement in helium-3 and how it leads to new kinds of surface states. You can have Andreev bound states, which could be Dirac fermions, or it could actually be, in special circumstances, Majorana fermions that are bound to the surface. Bosonic collective modes that kind of live within the bulk, even in the confined geometry. These multi-component order parameter leads to new stable superfluid phases, and you can make these arguments through quasi-particle scattering as to why they're stable and spontaneously breaks translation symmetry. So there are, all of these things have been looked at separately, but looking into the future, interplay between these surface states, these collective modes, and the domain wall formation, there's a lot to be done. I think John's hot on the trail of some of these questions, and we're working on some new results in this area as well that maybe we'll reveal in a few more months. With that, I'd like to thank you for listening, and I am happy to take any questions if there are any.
Okay, so if there are any questions, you can either raise your hand or you can just unmute yourself.
So why do we expect specular reflection to work here?
So you don't expect it to happen in physical systems, but some of the work that's been done has shown that Majorana fermions can actually live on diffuse surfaces as well. Specular reflection is just an easy theoretical assumption to make about the surfaces, but there's been work done with diffuse scattering and shown that you can still have survival of a lot of these aspects of quasi-particle scattering, domain wall formation, and this PDW phase. I mean, correct me if I'm wrong, John, but you're not expecting complete specular reflection in your devices, and still you see this new phase. So there's expectation it's not just specular reflection that would happen.
Yeah, just to follow up to that, and actually Alex has posted in the chat, is that it turns out if you put a little bit of helium-4 in your helium-3, it preferentially goes to the surface. If you put just 2 monolayers, this forms a superfluid helium-4 film, and it's been shown that you actually do get specular reflection in that case. So this was first shown by Mark Freeman in the Richardson group, in, I believe, 86, they did this. So yeah, this is an old technique that's totally possible. We just didn't do it in our version because causes some other problems.
But you still saw a new phase.
Yeah, and we do plan in the future when we're a little braver to try to do that pre-plating and make it specular.
Is there a way to increase pair breaking? Like, can I imagine, I mean, if I think about the simplest type of quantum phase transition, you can imagine Abakrotov-Gorkov, you have a regular superconductor that at 0 temperature is boring, and I break pairs and I can tune a superconductor insulator, or maybe superconductor to metal transition. Can I do that here? Is there a knob where I can actually ramp up the pair breaking to see some continuous quantum phase transition?
I don't know if there's a knob in experiments. I mean, I guess you could just make the surface that like very rough. I don't know, take some something to the surface and make sure it's a very rough surface. But I don't know if there's a continuous knob that you can turn that I know about. John, maybe you have a better answer.
Sorry, are you saying at the surface, Adrian, or are you saying in general?
Well, I'm just trying to figure out if there's a way that I could actually observe a quantum phase transition by fixing, let's say, the thickness of the slab and then ramping up pair breaking to the point where I destabilize a phase.
I could tune the magnetic field and I can eventually break Cooper pairs in a magnetic field. I'm not sure if that's a quantum phase transition. I've actually... yeah, I don't know if there's others. I mean, I can change the pressure. I can change the... So if I increase the disorder enough, I could actually probably lift the... you could probably lift the A phase off the phase diagram so it doesn't even happen at 0 pressure. Mm-hmm. So you could do a pressure-tuned quantum phase transition. Possibly, but it's a hard question.
Yeah.
I mean, isn't that phase diagram exactly representing a quantum phase transition at t = 0? Pressure tuned.
So it doesn't actually go to t = 0 in this diagram, but I think the expectation is that this A phase would continue all the way down to t = 0. Yeah, so you would have a quantum phase transition if you just tune the pressure. Yeah.
I mean, do you see signatures of a quantum criticality then?
Is that a question for me or John?
Anybody.
Okay. Yeah, I'm not sure.
What do you expect to see?
Well, you'd expect the normal signatures, the fan, right? You expect to see critical exponents. I mean, if it was a continuous quantum phase transition, but I think here that 0 temperature transition of bringing this line back would be first order, presumably.
It's a first order phase transition, so it's not. Yeah, the A to B is a first order phase.
Think of some way to use pair breaking out here, where you might have a chance for continuous transition.
That's right. But I don't actually know what the answer is between, say, the pair density wave and the B phase. I guess it's a first order phase transition too. So it must be because we see a jump in the superfluid density.
Mm.
Okay, any other questions? So I had one question. So throughout this talk, you considered basically the B phase, correct?
Yep.
So this might be naive, but what if we look at the A phase?
Yeah, that's a great way to approach it. So right now we are considering, we're trying to explore the PDW phase by assuming we are sitting right here and then kind of, nudging it over this way. But it should be the exact same procedure if we sit over at this this line and then assume that we're right at this edge of this transition. So you should be able to do the exact same analysis of what are the collective modes that are in the A phase, and can we use them to figure out what happens in this PDW phase? You can also think about, the collective modes. I don't know if there is anything like what the bound states are in the A phase. I haven't looked into that. But yeah, this kind of analysis still holds whether your starting point is here or your starting point is here.
Okay. Any other questions? Okay, so if not any more questions, let's thank Pramodh again.
Excellent. Thank you, everyone.